Okay, we're going to continue on with our study of current and voltage. In this section of the lecture, we're going to be going over some review of mathematical axioms that you're going to need to know in order to be successful in the class. I'm betting that most of you are familiar with these things. Most of you have probably had algebra. Some of the things I'm going to go over precede algebra. So if you already know it, please be patient, because there are a few folks in every class that either need a review or have just never had it before. Okay? The first thing that we're going to review are going to be exponents. Okay, exponents. Let's talk about exponents. Now, exponents are used a lot in the study of electrical engineering technology, and all we're going to do is, in this case, a basic review of the definition of exponents. So if I were to put on the board a number like this, 2 to the 7th power, okay, let's talk about what we're looking at. Okay, this number 2 right here, if this whole thing is written as an exponent representation, this number 2 is known as what? This is known as the base. Okay? And this number up here, number 7, the number that it's raised to, is known as what? This is known as the exponent. Okay? Now, when we write a number like 2 to the 7th power, if we were to drag it out and not just say what the answer is, because we probably all have our calculators by now, and we can plug it into our calculator and just say, oh, here's the answer. Okay? If we were explaining what that really means, 2 to the 7th power, who can tell me what 2 to the 7th power really means if we were to drag it out? It means 2 multiplied by itself this many times. So we're going to have 7 2's. 1, 2, 3, 4, 5, 6, 7. And we're going to put a little dot in between each one of the 2's. And what does the dot represent? Multiplication. Okay? The reason that we don't use x for multiplication, does anybody know? It's a common variable in algebra. So it would be easy to get mixed up if we had an algebraic expression if we were using x's to indicate multiplication instead of dots. Okay? And so we use dots to indicate multiplication. Okay, so who can tell me what 2 to the 7th power is equal to? What's 2 times 2 times 2 times 2 times 2 times 2 times 2? That is 128. Okay? So, did everybody come to the class pretty much understanding exponents? No questions? Okay? If you do, don't be embarrassed. You know, you can always ask me. I'll move through this rather rapidly because I do expect that most of you know the fundamental math review that we're doing. The second thing that we need to talk about are roots of a number. Okay? So one of the most common roots of a number is what's known as the square root. Okay? So if I wrote down the square root of 4 without blurting out the answer, what am I really saying when I write down the square root of 4? Perfect. What number times itself equals 4? And the number times itself that equals 4 is 2. Because 2 times 2 equals 4. Okay? Now, there are other roots of numbers that are a little bit more complicated. Okay? With a square root, what is it that is assumed on the left-hand side of the equal sign that I didn't write down? 2. It's assumed that there's a 2 right there. And that's what tells us that it is a square root. Okay? But it's used so commonly that they just, don't write the 2. But if I had a number like this, which let's say was the 4th root of 10, what would that be equal to? Well, let me tell you 2 things it would be equal to. One thing that it would be equal to that some people don't know, and maybe everybody in here knows, is that this is equal to 10 to a fractional exponent. Any idea what the fractional exponent would be? 1/4. That would be 10 to the 1/4 power. Okay? Does anybody know how to put that in their calculator and figure out what the 4th root of 10 is? I'm sorry, what?
10 raised to the 25 power.
Well, yeah, that would be the same thing as 10 to the 1/4 power, right? But I'm saying if you were to take it to a numeric value, a decimal value. So this is something that maybe you can look at. If you're not sure how to do it and the book doesn't do a good job of explaining it, go online. Go to Google, type in fractional exponents. And you'll see some really cool examples and explanations as well as some applications. Okay? I don't want to spend any more time on that, mainly because we will never use this in this class. Okay? Okay. Powers of 10. Okay. Now, in the study of electrical engineering technology, we are constantly taking big things and trying to express them in a very compact way. We're also taking small things and trying to express them in a very compact way. Example, if you have a capacitor that's 92 picofarads, you don't want to write out all those decimals. I mean, all those zeros on the right side of the decimal. Okay? What you want to use is you want to use powers of 10 in conjunction with either engineering or scientific notation, so that you can take that very, very small number and you can write it down by only having to write 3 or 4 things, not having to write, 15 zeros. Okay? Number one, because it doesn't look very clean, but more importantly because you will tend to make mistakes if you write 0, 0, 0, 0, 0, 0, 0, 0, 0. You're going to make a mistake. Okay? Okay. So let's say that we had a number like 4,100. Okay? And we wanted to write that as a power of 10. How would we write that as a power of 10? One way that we could do it is we could write 41 multiplied, and this is one case where I'll use x. Well, I won't use x. I'll use a dot. 41 times 10 to what power? Squared. To the second power. Are those equal to each other? Yeah. This is also typically written as 41 times 10 squared. That's probably the most typical way that it's written. Okay? Powers of 10 are used extensively in the study of engineering and electrical engineering, technology, and electronics. What if I had a number like this? 0.12345 1, 2, 3, 4, 5, 6 zeros, and then 834. How could I write that so that I had less of a probability of making an error, it took up less space, it looked cleaner, and it looked like I knew what I was doing? What did you do it as?
Oh, yeah, 10 to the negative 7.
What?
8.34 times 10 to the negative 7.
8.34 times 10 to the negative 7th power. Now, this is how you check it. Okay, I just took that from the audience, and I'm going to check it. Okay? You take the decimal, and you go 1, 2, 3, 4, 5, 6, 7. Got it. Okay? Would it be correct to also write this as 0. What is this? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 834. What if I wrote this as 834 times 10 to the negative 9th? Well, we got to check it. Let's check it. This is how you check it. Take your decimal. In the nursing department, my wife went through the RN program here. They call it the decimal dance. I always thought that was kind of funny. I guess they do some silly little thing where they dance around the room and then, they try to make their math easy. But anyway, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the decimal point would go on the right side of the 4, and that's where it is. Implied. Okay? Times 10 to the number of times I moved it. 9. Okay? Let's take a look at scientific notation. And then let's compare and contrast that to engineering notation. Difference. In the study of electrical engineering technology, you will rarely, let me emphasize that, rarely use scientific notation. You will, for the most part, always use engineering notation. So let's look at the difference. Scientific notation. Okay, so here's one example of scientific notation. Same thing we did before. 4,100. If we wanted to express that as a power of 10, then we could do it many different ways. But one way we could do it is to write 4.1 times 10 to what power? 1, 2, 3. Third power. Okay? Let's say we had a number like 5,000 or 54,000. If we had 54,000, we could write that as 5.4 times 10 to the what power? 1, 2, 3, fourth power. Okay? And we could do others as well. But let me tell you what the difference between engineering notation and scientific notation is. The difference between engineering notation and scientific notation is that we always move the exponent on our power of 10 in increments of 3. So when we have a number at its base value, okay, and what do I mean by base value? What I mean by base value is volts, amps, ohms that do not have a metric prefix. Okay? Like milli, micro, nano, pico, kilo, giga. If there is no metric prefix in front of the quantity that you're writing, whether it's an electrical quantity or a mechanical quantity, it could be a force. If there is no metric prefix in front of the quantity that you're writing, then it is said by definition to be in its base value. Okay? So, let me ask you a question. What would be the difference between 1 volt, okay, and 1 volt times 10 to the 0 power? What is anything raised to the 0 power? 1. Anything raised to the 0 power is 1. It's a fairly extensive proof. So if you didn't learn it in math, then just take my word for it. And then if you don't believe me, go online and you can see the proof. Because there's lots of them there. But I won't take the time to prove it to you. But basically, these are equal to each other. 1 volt is the same thing as 1 volt times 10 to the 0 power. Okay? So if you have the exponent on your power of 10 at 0, then you are at base value. Okay? So let me give you an example of the metric prefixes for volts. Let's start out with volt. And this is the base value. Okay? Because it's times 10 to the 0 power. Okay? If we are using engineering notation as opposed to scientific notation, we are moving in increments of how many on our power of 10? Increments of 3. I see several people holding up 3 fingers. You can talk if you want. Okay? I won't shoot you till after class. I'm kidding. Okay? All right. So let's say that we had more than 1 volt. Let's say that we had 1,000 volts. Okay? So if we had 1,000 volts, then that would be 1 kilovolt. 1 kilovolt. 1 kilovolt has the power of 10 raised to what exponent? 3. So that's engineering notation going up. What about the next jump to take us to 10 to the 6th? Does anybody know what that prefix would be? Mega. Mega. So 1 mega volt would be 10 to the 6th power. Okay? We won't get too much bigger than mega in this class, but we will get smaller because we'll study capacitors, and capacitors get really small. Okay? So let's get smaller. Let's say that we had something that was 1/1000th of a volt. Very small voltage. Okay? Does anybody know what the metric prefix would be on 1/1000th of a volt? Milli. So that would be 1 millivolt, and that would have a factor of 10 to what power? -3. Good. 10 to the -3 power. Let's move down to, using engineering notation, let's move down to the -6th power. What would the metric prefix be for an exponent that's raised to the -6th power? Sorry? Micro. Good. That would be 1 micro, 1 microvolt, and that would be 10 to the -6th power. What if we moved even smaller? In engineering notation, we're moving in units of what? 3. 3, 6, 9, 12. Okay? So if we're moving to 10 to the -9th, 3, 6, 9, okay, what would the metric prefix be for 10 to the -9th? 9th. And that 9th nano, that's a good way to memorize it. is that, you know, ninth and nano kind of rhyme with each other. Okay? So 1 nano, N-A-N-O, 1 nanovolt would be a factor of 10 to the negative ninth, minus ninth. And finally, we go one more step in engineering notation. And what do you think the next step on the exponent would be? Negative 12. Good. And negative 12 would be, I already heard somebody say it, pico. So 1 pico volt would be a factor of 10 to the negative 12th power. So this is how we use the metric system, okay, to simplify the number of units that we have to write out to accurately represent how many volts we're dealing with. Sometimes with capacitors, we deal with picovolts, nanovolts, microvolts, millivolts, volts, kilovolts, megavolts. Okay? Now, the cool thing about the metric system is these prefixes and these exponents on the factor of 10 never change. They never change. All you have to do is put in a different unit. This could be, instead of millivolt, it could be milliamp, if you were talking about current. Okay? If you were talking about ohms, this could be milliohm. If you were talking about power, this could be milliwatt. Okay? The disparity or the difference or the contrast that I make between this system, which is sort of the universal system of measurement, is with the English system of measurement. Have any of you ever watched boxing tournaments that are held in London or England? When they announce a fighter, do they tell you how much he weighs in pounds? No. They tell you he weighs 13.2 stone. I don't even know what I don't even know how much a stone weighs. I mean, you know, it's in a book somewhere, but you know, and look how complicated it is just to deal with the measurements that we do around our house. Okay? How many inches are in a foot? 12. 12 inches in a foot. How many inches, or feet rather, how many feet are in a yard? 3. 3 feet in a yard. Okay? So you see that going from one unit to another unit is not a factor of 10. Okay? The conversion in the English system requires you to know that, you know, there's 12 inches in a foot, and there's so many feet in a yard, and so on and so forth. Okay? So, scientific notation, although it's perfectly legitimate and valid and used in a lot of disciplines, is not used so much in electrical. In electrical, we use engineering notation, and if we move over here, this is an example of engineering notation. You notice how the exponents are all multiples of 3, 6, 3, 0, minus 3, minus 6, minus 9, minus 12. That's engineering notation. You notice how there's no minus 2? You notice how there's no minus 4? You notice how there's no minus 10? If there were, then you would be expressing it in scientific notation. That's done a lot in medicine. In medicine, they use that a lot. You know, like centimeters. Centimeters or cc's. Those kinds of measurements are used a lot in a lot of other disciplines. But for us, engineering notation is what's really important. Now, the metric prefixes, which I've already given you a sample of, are something that you need to put on your crib sheets. Remember that for either the online folks or the in-class folks, every single exam that you take when you come in here, you get 2 8.5 by 11 crib sheets, front and back, with anything you want on it. You can put anything at all you want on it, as long as it's not, you know, offensive or obscene or pornographic or something like that, right? It's got to be applicable to the class. But you could literally take stuff from my notes, you could take stuff from the internet, you could take stuff from another book, you could reduce it and bring a magnifying glass, you know. But what you're going to find is, in the beginning of the class, you're going to have like Ohm's law take up a whole sheet of paper. By the time you're in the 4th week of the class, Ohm's law is only going to take up maybe this much of the paper, because you're going to have used it so much that you almost have it memorized. But, you know, it's good to have it there just in case you know, forget one of the formulas. Okay? And then by the time you get to the end of the class, you should have your crib sheet dialed in to the point that you want to keep it. You want to put it in a binder. Maybe put plastic on it. Okay? And toward the end of the class, I will make available on my web sheet a cheater sheet, which, you know, is more polished. I don't do that now because I don't want to cheat you of the experience of making up your own cheater sheet, because that's how we learn things. We learn things by hearing, seeing, writing. And if you don't write out your own cheater sheet and then rewrite your cheater sheet, rewrite your cheater sheet, rewrite your cheater sheet, you're not learning as much as you would be if you were doing that. Okay? All right. Just want to take a look at a couple of other notes that I have here to make sure I haven't missed anything. All right. There's something that you're going to read in the book, and this is something that you're not really going to use in the field a lot, but it is something that I'm required to go over with you. You will find it in my notes, okay? But it's the definition of what we call a Coulomb of charge. A Coulomb of charge. A Coulomb of charge is like a quantity of electrons. It's a quantity of electrons. Okay? Now, let's think about this for a second, and let me help you give this meaning. Imagine for a minute that you're looking at a plumbing system, and there's a section of pipe that is, you know, some kind of clear pipe. You know, it's It's like clear PVC. I don't know, what would you call that? Acrylic pipe, okay? Acrylic pipe. In other words, you can see through it. You can see the water going through it. Okay? And let's say that you've got a meter that's hooked on to this pipe, and it's an expensive meter, and it's very accurately measuring how much water is flowing through that pipe per unit time. Okay? What do you think a normal meter might read if it was measuring flow rate of water in units per time?
Gallons per minute.
Yeah, how about gallons per minute? Okay? So you've got, let's say, 5 gallons per minute flowing through this pipe. And you've got this meter, and you see the meter, and you know, you see that, yeah, the meter says I got 5 gallons per minute, and that's what it's supposed to be, so we don't have to change anything. Okay? Now, when we look at that water, what is that water really made up of? Water molecules, right? The water is really made up of H2O. What does H2O stand for? 2 hydrogen atoms bonded to 1 oxygen atom. Now, H2O can exist, well, primarily exists in 3 different states. There is a 4th state we won't talk about, but there's 3 primary states of water. What are they?
Liquid, solid, gas.
There's aqueous water, like what you drink. Fancy word for what you drink. Aqueous water. There's ice, which is a solid. And then there's vapor, right? Like a teapot, or, you know, a high pressure steam turbine. Okay? We'll talk about that later. We'll talk about that later. Yeah, it gets into plasmoids. The difference between the 3 states of water you can drink, aqueous, ice, and vapor. Does anybody know what the difference is?
The rate of movement of the electrons.
The difference is the bonds between the H2O. They're either broken or they're there. Let me give you an example. How many of you have ever opened up a dishwasher, like right after it's done, and it's all full of steam? Or some other device, you know, that's got steam in it. And you open up the dishwasher, and all of a sudden, all this steam just starts rising. And maybe it, you know, your arm's real close to it. Would it be fair for me to say that it would be really easy to get burned if you had your arm real close to that steam and you kept it there?
Yeah.
Okay? Do you know why that is? The reason that is because when the water was turned into vapor, there was energy that was required to break a hydrogen bond in the H2O. That energy is stored in the vapor. When you put your arm in the midst of the vapor, your arm is at a much cooler temperature, because vapor is at a hot temperature, right? Much hotter than your arm. So what happens? The water starts to collect on your arm and immediately begins to condense. In other words, it starts to get a little bit wet. The energy that went into breaking the hydrogen bonds and making the aqueous water vapor is now returned to your arm. And that's the reason that steam burns are so dangerous. Okay? Now, when you're looking at this water, and you see this water going by, all right, let's just imagine for a minute that there was, you know, some kind of a little hatch door or something on the pipe, you know, where you could open it up and you could actually reach down into the flowing water, you know, and you could take a cup, right, and you could scoop some water out of the pipe, and now you got some water in the cup. Maybe you drink it or whatever, okay? If you had, let's say, a measuring cup that you would use in your kitchen, okay? Would it be fair to say that you could reach down there and you could scoop some water out and you could look at the hash marks on your measuring cup, and you could, you know, pour some out and you could get it to where you had exactly 1 cup of water? That would be fair to say, right? Okay? So you could say, hey, guess what? I've got 1 cup of water. But what is it that you really have if we're talking at the atomic level? You really have a whole bunch of H2O molecules in the aqueous state. That's what you really have. So then the question becomes, how many water molecules are in a cup of water? Well, yeah, you can measure it in moles, okay, but you can also measure it in molecules. You can also measure it in molecules. Now, most people don't care. It's like, who cares? Okay? But the fact of the matter is, you know that water is made up of H2O. You know that that cup of water that you're getting ready to drink, or whatever you're going to do with it, is made up of H2O molecules. But if somebody were to ask you to count how many H2O molecules were in that cup of water, even if it was see-through glass, can you see an individual water molecule? No, you can't. You cannot. It's the same kind of thing in the study of electrical engineering technology. When we're talking about electrons that are flowing through a wire, okay, we talk about the whole issue of the Bohr model, subatomic particle theory, and the specific electrons that flow through the copper wire. Which electrons are those? Valence electrons. Valence electrons. So we have valence electrons flowing through the wire. But let's say that we were to take a snapshot of a piece of wire that was carrying 600 amps. So we knew that there was 600 amps flowing through that wire. How did we know that? We had a Hall effect clamp-on meter. Open that drawer, that top drawer right there, and pass me, no, the one in the bag. Pass me the one in the bag. This is what we call a Hall effect clamp-on current meter. Okay? So we can turn this thing on right here. Obviously, I don't have anything to measure with it right now, but there's a way to open up this loop right here. Okay? The purpose for that is so that if there's a wire, okay, we can take this loop, we can open it up, put it around the wire, and close it. Well, in every wire that's carrying current, there's something that's circling the wire. Does anybody know what that is? It's a magnetic field. There's a magnetic field that's circulating the wire. That's where the energy is stored. Okay? But the fact, but that is just how this meter works. I mean, it's kind of like magic in a way, if you don't understand the theory. Because really what you're doing is you're taking this thing, this meter, and you've got this wire. Just pretend like this pin is a wire. You've got this wire, and you're opening up this meter, and you're putting it over this wire, and you're closing it, but the wire isn't even touching the meter. So how's it measuring anything? Well, the way it's measuring something is because there's a magnetic field around the wire. And it uses a phenomenon called the Hall effect to measure the current. And these are used all the time. I mean, if you're an electrician for PG&E, trust me, you'll have one of these in your tool pouch. And when you go up to a circuit, one of the first things that you'll do is you'll find a cable, and you'll go up to it, and you'll clamp it on, and you'll go, oh, okay, that's dead. Or, that's something I don't want to touch. That's got a lot of current in it. Okay? So let's say that we checked out this meter. We checked out this wire, and then we looked, and we saw that, aha, there's 600 amps. 600 amps of current flowing in the wire. Okay? The question then becomes, if we were interested or somebody asked us to explain to them, how many electrons is that? It's kind of like somebody asking us, how many H2O molecules are in that cup of water? Who cares? Okay? But it's something that we learn in the basic study of electronics. A Coulomb is a quantity of charge. A cup is a quantity of water. If I tell you I'm going to give you 1 cup of water, you can kind of visualize that. You know, you've seen it before, and you know how much you're going to get, and it's okay, whatever. Okay? 1 Coulomb, check out these numbers. 1 Coulomb, I'll just abbreviate C-O-U-L. It's also abbreviated as a capital Q in a lot of books and manuals. 1 Coulomb of charge. The reason we say of charge is because when we have a big clump of electrons all gathered together, we have a negatively charged ball of energy. Okay? Now, it may not be in a ball, it may be going through a wire. Okay? But we've got a big clump of negatively charged energy. In 1 Coulomb, there are 6.24 times 10 to the 18 electrons. You know how big that is? 6.24, excuse me, 6.24, let's move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, comma, 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 1, 2, 3, comma. Anybody want to tell me what that number is? That's a big number. I'm not quite sure what that number is. That's a lot.
It's a duplex.
Okay? The point here is that an electron is there. I think I have my sound back now. An electron is extremely small. Nevertheless, when we talk about current that's flowing through a piece of wire, we need to understand what it is that's happening. A very small subatomic particle that can't even be seen by the human eye, just like a water molecule can't be seen by the human eye, okay, is flowing in huge numbers through the wire to do something useful. Run a hairdryer, run a microwave oven, run your TV set, whatever. Okay? Now, are we okay down here? Let's talk about what the definition of an amp is. An amp is shorthand for ampere. Okay? So when somebody says, you know, there's 10 amps flowing, the longhand definition of amp is ampere. 1 ampere is equal to 1 Coulomb per second. So just 1 ampere. 1 ampere has this many electrons flowing by a stationary point every second. This is an unfathomable number. I think it would be fair to say that probably if we took everybody on the whole campus and we all lived to be 100 years old and we added all of our lifetimes together in seconds, we wouldn't live this many seconds. I haven't done the math, but it's a big number. For all I know, it might be the state of California or it might be the country. I don't know. I haven't done that. But I mean, it's a huge number. I don't even know what this 6 would be called. Okay? So when you talk about amperes, just be aware of the fact that you're talking about gazillions and gazillions and gazillions of electrons that are flowing through a conductor. But what kind of electrons? Valence electrons. And why are valence electrons flowing instead of electrons that are closer to the nucleus?
Because they don't have the gluon.
Well, it's not gluon, it's because they're not held as tightly. Remember that the stuff in the nucleus is positively charged. The stuff outside the nucleus is negatively charged. Okay, so they're opposites. They attract. So the nucleus is attracting the electrons, trying to keep them close. So the only electrons that can escape are the ones that are on the very most furthest orbit. And that's only with certain types of materials. It doesn't happen with rubber. Right? Rubber we use as an insulator. Can't use rubber as a conductor. And the primary reason falls into subatomic particle theory. How many valence electrons are there in a rubber atom? It's very different than how many valence electrons there are in a copper atom. Okay? All right. Anybody have any questions? Sir?
Is that just a random number, 6.24? Where did that come from?
6.24? Well, I have to believe the people that write the books and the journals and the scientists. But from the schooling that I've had, Cal Poly, USC, Pepperdine, this is a universally agreed upon number that is verifiable in a laboratory that has instrumentation that's much more expensive than we have here. So if you worked for like Bell Labs, you know, they can verify this. I don't know where it came from. Is some scientist figured out some instrument that they could build and some techniques that they could use to measure this. And when they got done measuring it, this was the number that they got. You know? And then probably somebody in Russia was doing the same thing, and then when they met at a conference, they went, "What did you get?" "Oh, I got 624 whatever." "Oh, I got 624 whatever." "Well, how many zeros did you get?" "Oh, I got the same number of zeros," right? So, you know, that's the way that it becomes universally accepted. And the reason I can say with certainty, or some high degree of certainty, that it's accurate is because it fits the scientific model. In other words, it's repeatable anywhere on Earth. So if you have the right instrumentation, you have people that are trained with the right skills, then they're going to come up with the same number. And that's the reason it's published in all the books and all the journals, and it's a universally accepted number. It's not a number I came up with. It's in the book. That's a good question. It's not a number that we can measure in this lab. It takes, you know, it takes very, very sensitive equipment. Okay? All right. Well, that concludes Part B of Week 1. And if you have any questions or need anything from me individually, feel free to come up and talk to me. Otherwise, have a safe drive.